Okay. So here are the steps. First of all, it says we're going to find the derivatives and the domain. We'll find f prime of x and f double prime of x. Note the domain of the function. Okay, when we get ready to sketch the graph, we'll look at critical values of f. We're going to find critical values by solving f prime of x equals 0 and finding where f prime of x does not exist. We already know that. These numbers yield candidates for relative max and min. We'll find the function values at these points. Our goal here is going to be to eventually graph these things. We want to use our first derivative test to determine where it's increasing and decreasing, or where we might have any relative extrema. Okay. Then we're going to look for inflection points, concavity, and then finally we're going to sketch the graph. Okay. So let's see if we can do that. We've got a few things we want to graph. Let's start with f of x equals x cubed minus 27x. Okay, x cubed minus 27x. Okay, first thing we're going to do is think about, like they said, the domain of this function. For our particular function, it's a polynomial, so it's defined where? All real numbers, right? We can put anything in there, so that's good. Okay, so we'll go ahead and take a look at the critical values. So f prime of x is equal to what? Okay, 3x squared minus 27. I'm going to set this equal to 0. I can factor out a 3. So this factors is what? That's right. Okay, x minus 3 times x plus 3 times 3. And so we're going to set each of those equal to 0. We get critical values are x equals 3 or negative 3. Very good. Okay, these are our critical values. All right. So they suggest that we go on and figure out, because we're going to plot these eventually, what the y-coordinate is as well. So if I plug 3 back into my original function, f of 3 is equal to what? Minus 54? Okay. All right. And then f of negative 3 okay, so f of negative 3 is 54. All right, so at least in our graph, we know 2 points so far. Okay, we need to know if these 2 points are max or min. So we're going to look at the what? The easiest thing to do is to look at the second derivative, okay, which is not 9, but 6x. Very good. So f double prime of 3 gives us 18, or it's positive. Okay, so we know we're going to have what? There, relative max or relative min? Relative min. Okay, and then if we look at f double prime of negative 3, we get what? Negative. And so we get a relative max. Okay? So if we try to sketch that information so far, this will be a rough sketch. So we know that we've got a point at 3, negative 54. So about right here. And we said that that particular point at 3 was going to be a relative min. So that means it was concave. We can kind of make a note to ourselves that right here the function should do, because it's concave up there. Okay, does that make sense? All right, just kind of making a note to ourselves about what this might look like. Okay. Then at -3, we said the function's going. Okay, we're going to have a relative max. It was concave down. Okay, so I'm going to make a note like that. When you put those two things together, if we can, that already gives us a sense of what this graph right in here. Okay, so we've already got some feel about what's going to happen. The other thing we might want to do is actually figure out where the function is going to cross the x-axis and also the y-axis. So to figure out that information, which function should we look at? The original function. Okay, we could figure that out just from our original function. So let's look back at f of x equals x cubed minus 27x. First of all, if I put 0 in there, we get out what? 0. Okay, so I know 0 is a point on the graph. Okay, and if I set this thing equal to 0, factor off what? Factor off in x. We're left with x squared minus equals 0. And we could solve that by saying x squared equals 27. And so x is going to equal what? Plus or minus the square root of 27. Okay, so that's where we're going to cross the x-axis. Okay, we're going to have a point at, or 2 points, at plus or minus root 27, 0. Okay, square root of 27 is about how much? Okay, 5.19. Okay, so we're going to have a point at 1, 2, 3, 4, 5.19. We'll have a point here. And then also at minus 5.19 here. Okay. Is that enough for us to sketch this graph? Okay, looks like it. Because we know on the ends, you took Math 110, we talked about end behavior of the function, right? Eventually, in a polynomial function, it's going to continue to go up or down or something like that. So here, I think our graph will look something like this. I want it to go through that point, but I think you get the idea. And we were able to do all of that without having to graph it on our calculator. Okay, which is what I'm going to expect you to do on the test. Yes. All right. Okay, we really didn't talk about the inflection point. It's where we changed from concave up to concave down. So we would have gotten that from our second derivative by setting it equal to 0. Okay, and obviously we get x equals 0. And so you can see right here that that's kind of where you can say, yep, it was concave down, and then about here it changes to concave up. Okay. Yeah, now I'll just be looking for, these things over here to match up with what you have here. Yes. Mm-hmm. All right. Other questions? Okay, very good. So that wasn't so bad. F of x equals 2x cubed minus 3x squared. Okay, so the first thing we probably could go on and start with finding the zeros of the function. Okay, that'll help us since we've got to do that anyway. So when we look at f of 0, we get what? 0. Okay, so that's the point. And then if we set this function equal to 0, okay, we can factor off x squared. We're left with 2x minus 3. Okay, so we get, on our graph, we know we're going to graph 0, 0, and also 3/2, 0. Okay, those are two of our points. All right. Okay, so we're going to have something at 0, 0, and also at 3/2, 0. All right, now let's see if we can find those critical values. Okay, we're going to look at the second derivative. And the second derivative is what? Okay, 6x squared minus 6x. Very good. Okay, if we set this equal to 0, we can factor out 6x. We're left with x minus 1. Right?
How is the second derivative? That's the first derivative.
I'm sorry. Okay, the first derivative. That's what I meant. Sorry. Okay, that's my first derivative. All right, we set it equal to 0. We get x equals 0 or x equals 1. Okay, these are my critical values. Okay, these are the critical values. All right, if we want to, we can go on and figure out what their y coordinates are by plugging back into the original function. So if I put 0 in, I think we already know we get out what? 0. Okay, so we get 0, 0 for this one. And then if we plug in 1, we're going to get what? Negative 1. Very good. 1, negative 1. Okay, so those are, well, really one more point that we can plot. Back into the original function. Anytime we want to, graph or figure out what the y value is, we have to put it back into the original function. Okay, so we got 1, negative 1. Okay, now we need to know, is this thing concave up or concave down at these points? And so that's where we do f double prime of x. We got 12x minus 6. Okay, if we set this equal to 0, well, we need to do what? Plug these in, or the critical values in here. F double prime of 0 equals negative 6, which means it is concave down, but we have a relative max. Okay, relative max. So at 0, 0, we can expect the graph to look like cap like this. Okay, then if we look at f double prime of 1, is it positive or negative? Okay, positive. And so we're going to have concave up, which means it is a relative min. Okay, relative. All right, so at the 1 negative, it's going to do something like this. Okay, so we already know what's going on there. And I think that's probably enough for us to graph this one. What do you think? Right. Okay. Okay. So it's like that. Questions about that? Okay, good. That's fine. Yeah, if you left those off, I'd be okay. Okay. But that is correct. Yes. Okay. Other questions? Okay. Very good. All right. You want to try one on your own before we move on? Yes. Let's do that. Okay. Matthew? No, let's do his name. What's his name? His name. Yes. Will. Is this what you got for the first derivative? Okay. Got it. Okay, good. Oh, yes, it should. Okay, good. All right, 4x cubed. So in that case, we can factor out 4x, but we're left with x squared minus 3. Okay. All right. I knew you had something different from what I had. Okay. So x equals plus or minus the square root of 3. Okay. 1.3. Okay. So we can go on if we want to and figure out what those values are. The first one is what, negative 9? They're both negative 9. Is that right? Okay, plus or minus square root 3, negative 9. Okay, if we put in 0, we already 0, 0 plotted. So the original function. So we get, okay, 1.73 is about here. We're going to go plus minus 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3. Okay.
Do the math on the left-hand side,
Uh-huh.
but I can't take that information and do anything with that little.
Okay. Well, all right. So, way cool graph. Okay. First thing we did was found the zeros. Okay, so we got them plotted. Now we've got critical values, and just we know they're important points, so we're going to go ahead and find their y values and plot them too. So we've got, these are the points. We've got 0, 0, which is already plotted, and then we got positive square root 3, negative 9.
Since 0 and 0 is already plotted, so that x equals 0 really doesn't mean anything, right?
Well, I think it does. It's still a critical value, and we kind of expect that maybe it's a candidate for a relative max or min. So that's still going to be important, because this is coming from the first derivative. So yes, it's still important. Okay? So I'm going to plot the points, minus 1.73 to negative 9. So yeah,
On the homework, it had us like give one or two different types of answers, whether it becomes a radical or a decimal. Which way you go?
I think in order for you to graph it, you've got to convert that radical to decimal, just to kind of approximate.
We write it down.
If you were reporting it, I'd probably do this. If you were, let's say we were talking about something was a maximum profit, I wouldn't expect you to leave that as square root of whatever. So, but all about the same. Okay. All right, so we got that. So the next thing we want to know is, are these things relative maxes or relative mins? So I'm going to look at my second derivative.
And why didn't we care about the positive 1.7?
Well, we did plus n minus square root 3. So let me add a little. Maybe. That's okay. Okay, well, if that's good, that's fine. Okay, second derivative is 12x squared minus 12. Okay, so we can factor off a 12. Right? And this factors as basically x minus 1 times x plus 1. Get x equals plus minus 1. And my head is on autopilot this morning. I didn't have my coffee. What we really needed to do was plug our values in here to determine if it's concave up or concave down. Okay, please forgive me. I don't know. We might have to. But f double prime 0 gives us a what? Negative, okay, which means it's concave down, which means we have a max, okay, relative max. Okay, so at 0, then I have a relative max, which means this thing is going to cap like that. A maximum would be up here. Okay, then if I look at f double prime of negative square root 3, okay, if I put that in, that's going to give me 3 times 12, which is 36. That's going to be positive. Okay, which says we have a relative min. This negative 3, I'm going to have a relative min here. Okay. And then I think the same thing is going to happen for positive 1, right? Yes. Okay. So we have a relative min here as well. All right. So do we have some idea about what this should look like?
Yes.
Yes. Okay. All right, it's going to look something like, which shouldn't be a big surprise. From Math 110, remember some of the things that you learned about graphing? First of all, Math 110, college algebra, the fourth degree polynomial, how many zeros should it have? 4. All right. A fourth degree polynomial should have 4 zeros. A fifth degree polynomial should have 5 zeros. Some of those things we call repeated zeros. So 0 in this case is repeated. We had x squared equals 0. So it was 0, 0, and then plus and minus square root 6. Remember talking about when the graph was going to touch the axis versus cross it in Math 110? And it's been a while since I taught Math 110, but I'm pretty certain you all should have talked about those things. If we had, remember, if the 0 had an odd multiplicity, it would cross the graph. I think that's what I recall. Okay, and then if it had so with the plus and minus 6, they only appeared once, each of them. So we actually cross the graph at that point. But for 0, it's got an even multiplicity, so it just touches the graph here. Okay, that's just, if you remember that, that's great. If you don't, then that's okay too. Okay, yes.
On the relative min, relative max, you plug in this point into the second derivative.
To determine where a relative min or max occurs, we can plug values into the second derivative. To actually find out what that max or min is, we have to plug it back into the original function. So if I were to ask you what is the relative minimum, we would say -9. It happens to occur, though, at plus and minus square root 3. Okay. All right, how many people got close to something like this when you tried to graph it? Okay. Another example? Okay, that's fine. I might. So it could be a separate question. I think, in these types of graphs, if you don't, it's pretty much almost drawn itself. So we kind of know. But, you do need to know how to find inflection points, but not necessarily to graph. Okay. Alrighty. I'll let you try another one. Yes. Okay.
When you have something now, the 9 does not have an x, how you do it, always still click how you break it down and roll through the 9 over.
When we're factoring,
Yes.
when we want to apply this zero factor property, everything has to be set equal to 0.
Okay.
Yeah. The only time, especially if you're talking about a squared thing, that we would move something to the other side is if we only have a square term and a constant. You could do it.
But in this situation,
We got a middle term, so we wouldn't do that.
so you have to make sure. Like I see.
Okay. I also note, I don't know if you remember, but when we tested using synthetic division, we tested 1 to see if it was a 0. Remember the remainder was 5? Do you remember there was a theorem that said when we plug this thing in, whatever the remainder is, that's actually the same thing as f of that value? Okay. Just making some connections. If you remember, great. If not, then that's okay. All right, so let's talk about these things. So we got okay, f of 0 is 1. F of 3 is also 1. And f of 1 is 5. Okay, that's what we have so far. All right, we weren't able to find the zeros, but we could plug 0 in to figure out where it crosses the x-axis, or rather y-axis. And that's going to be good for us. All right, now we need to know if these things are relative maxes or relative mins. And so I'm going to look at my second derivative. 6x minus 12. And then I'm going to plug in 3. I get positive, right? Which means this thing is concave up, which means we have a relative min. Okay? If I look at f double prime of 1, okay, we put 6 times 1 is 6 minus 12. That gives us negative. So it's concave down, which means we have a relative max. Okay, so at 3, 1, we said we're going to have a relative min. And at 1, 5, a relative max. Okay, so the function looks something like, whoops, something like that.
So you wouldn't test the 0, 1.
No, because it was not a candidate for a critical value. The only ones we got for critical values were 3 and 1. Okay.
Could there possibly be another 0 on the x-axis?
What do you mean possibly?
So is that the only place where it crosses the x-axis?
Based on what we have, yes. Okay, and I said earlier that there are 3. If we're talking about a third degree polynomial, we'll have 3 zeros. But remember, some of those zeros could have been complex or imaginary. And so in that case, they would not cross the x-axis. All right. Okay, other questions about that? Oh, starting to get better. Good. Okay, good. All right, well, keep on practicing on that. We'll stop here. Next time we'll continue graphing. We're going to look at those rational functions.